So vector calculus. First of all, we will discuss all the topics one by one, why vector calculus is needed in the machine learning, and what are the applications, and then partial derivatives, and we will go through each and every topic up to the topic of gradient of matrices. So I will start from here. Vector calculus, it is concerned with the differentiation and the integration of the vector fields. That is the vector calculus.
Your screen is not visible actually at PDF.
PDF is not visible now. Now is it visible?
Priyanshu, is it visible to you?
No, sir.
1 minute, sir. I will.
Yeah, now it is coming. Now I can see it.
It is coming.
Yeah, it is coming now.
Okay. Can I start now? Okay. So why to need the vector calculus in the machine learning? So as we know that the machine learning is the subfield of the artificial intelligence, which is totally based upon the data. So in order to train the data of the computer, we need the vector calculus, because many algorithms in the machine learning optimize an objective function with respect to a set of desired model parameters. So to control how well a model explains the data, we need the gradient. In order to find the optimization of the objective functions like maximum and minimum, we need the gradient. So the vector
सर वीडियो ही नहीं आ रही है. हेलो
हेलो
सर, मैं स्क्रीन नहीं देख पा रहा, मतलब आ नहीं रही है शेयर. अब आ रही है. कूल.
ओके, कंटिन्यू.
अब आ रही है सर?
हाँ, यस सर.
अभी मुझे नहीं दिख रही है.
1 minute, I will share again in 1 minute.
You just share the PDF instead of sharing your whole screen.
Now I think it is visible. I have just shown this tab.
Yes. Yeah.
Okay. So many algorithms in the machine learning optimize an objective functions. That's why the vector calculus is needed in the plays an important role in machine learning. So let us see some examples in which the vector calculus plays an important role, like linear regression, curve fitting problems, and optimize linear weight parameters. It optimizes the linear weight parameters. The second one is the neural networks. It minimize and reconstruction error by repeated application of chain rule. And the third one is the Gaussian Gaussian mixture models, where we optimize the location and shape of parameters of each mixture component to maximize the likelihood of the model. So these three examples we will discuss in the upcoming chapters. So I have just giving the overview of these examples that the vector calculus is needed in these problems. So to implement the above problems, we need the partial derivatives, that means the gradient of function. So therefore, vector calculus is one of the fundamental mathematical tool we need in the machine learning. So we have to find the gradient. First of all, we will discuss about the functions like univariate functions. In the univariate functions, how to find the differentiation. This is the topic. First one, that is nothing but it is the differentiation. Let us take a curve y is equal to fx, in which our x belonging to R, whose dimension is 1 only. So there is only one domain, one variable x. So this is the curve. Let us say this is the point x naught. At x is equal to x naught, this is x plus delta x, x naught plus delta x. and this is the secant which is intersecting these curves at the 2 points. So in order to find the slope of this secant, we will do the y2 minus y1 upon x2 minus x1, that is f of x plus delta x minus fx upon delta x. This is the slope of secant. The difference quotient computes the slope of the secant line through 2 points of the graph of f. As we have seen, through these 2 points f of x naught and f of x naught plus delta x, we have find the slope of secant in this formula. So but the difference quotient can also be considered as the average slope of function f between x and delta x. In the limit, if we put delta x tending to 0, we obtain the tangent of f at x. If these 2 points difference is becoming 0, then this line, secant line, will becomes our tangent. So the slope of tangent at any point gives us the derivative of the function at any point x. So this is nothing but, if f is differentiable, then the tangent is the derivative of f at x. So definition of the derivative here, it comes out to be, it is the limit of the difference quotient where we will put our delta x or h tending to 0. We get the derivative of that function at any point x. And the secant in the above will become the tangent. So we have find the derivative of a function, basic definition of the derivative from the secant line of a function. Now we will move forward towards an example how to find the derivative through the basic definition, limit h tending to 0, f of x plus h minus fx upon h. This is we will put in this function f of x plus h, then we will solve fx plus h whole power n minus x power n upon h, and it can be written as binomial experiment.
You can skip, actually these are very basic things.
Yes sir, I will skip these things. So Taylor series, should I continue?
If it is multivariable, you can continue. Otherwise,
Okay, from multivariable I will continue.
okay.
Yes, from the gradients I will continue. Partial differentiation and gradients. So till now we have seen the derivative which is applicable on the single variable functions. In this, the generalization of the derivative to the function of several variables, that is the gradient. For the multivariable functions, we find the gradients. The gradient is nothing but it is the collection of all the partial derivatives. It is a collection of all the partial derivatives. Now the partial derivative of a function f r to the power n to r, here our x domain, our domain is multivariable. Its dimension is n. So x belonging to r to the power n of n variables, x1 to xn, we can assume. Then we can find the partial derivative of each partial derivative of the function with respect to each variable from x1 to xn with these formulas we have seen in the derivatives, and collect them in a row vector. As we know that the gradient is nothing but it is the collection of all the partial derivatives. So del f by del x1, del f by up to del f by del xn, we can collect in a row vector that will becomes the dimension of 1 cross n matrix. This is the gradient of f in the case of when our function is r to the power n to r. So this is the gradient where n is the number of variable and 1 is the dimension of the range. Example, this is the f of x1, x2. Firstly, we find the partial derivative with respect to x1, then x2, and then we can collect them as a matrix, which becomes 1 cross 2. And another concept in this partial derivatives of the multivariables, that is the chain rule. When to apply the chain rule, if our function, let us assume that it is two variable function from R2 to R of two variables x1 and x2, where the both two variables are themselves a function of t, where x1 is a function of t and x2 is a function of t. To compute the gradient of f, we will apply the chain rule as this. First of all, we find the derivative with respect to x1, x2 in a row vector because it is a gradient. Then again, what we will do in the second matrix, that is because x1 is also a function of t, so we'll find the partial derivative of x1 with respect to t and partial derivative of x2 with respect to t. So on multiplying these two matrices, we will get our gradient like this, del f upon del x1 upon del t plus del f upon del x2 upon del t. This is the gradient when the variables are also a function of some variable t. So this is the example of this f1 x2, f of x1 x2 given, x1 is given, x2 is given. Then we can find the, using the formula, we can find easily calculate the gradient of this function. That comes out to be this by using this formula. Now nextly, in this concept, if x1 x2 function of x1 x2 and x1 and x2 are themselves a function of multivariable, consider two variables s and t. In the previous one, x1 and x2 are only the function of t, but here the x1 and x2 both are the functions of two variables s and t. So in this case, how we find their partial derivatives? This is the main concept. So first of all, we have to find del f upon del s. We will differentiate with respect to x1 and then x1 with respect to s. If we find the partial derivative of with respect to s, then we can use this formula. If we find the partial derivative of f with respect to t, then we can use this formula. Firstly, we will respect with x1, then x1 with t, and then f with x2, then x2 with respect to t, and so on. It depends on how many variables are involved in this function. So then the gradient is obtained by the matrix multiplication. So this is the representation, matrix representation of our gradient. We can involve in this case df upon d of st, that gives this matrix multiplication of rows and columns. Gradient of vector valued function, this is our next topic. In this case, our domain is also of n dimensional and output range is also m dimensional. This is m dimensional and domain is n dimensional. So let us consider a vector x, that is our domain vector, x1 to xn transpose, that is n dimensional vector. The corresponding vector of the function is given as f1x to fmx, that is the m dimensional vector. So what we have to find? We have to find the gradient of this function. Then therefore the partial derivative of a vector valued functions. So first of all, we know that the gradient is nothing but it is the collection of the partial derivatives of this with respect to each variable. So we are doing the partial derivatives of this function r to the power n to r to the power n with each xi, where xi is each variable of the domain, and I gives 1 to n, because we know that the n is our dimensions, is given as del f upon del xi, it is equal to del f1 upon del xi, del fm upon del xi, because we have, in this case, we have f1 to fm, there is m dimensional function f. So we have f1 to fm are the functions possible here. So we have to differentiate each with respect to xi. So this will give us del f upon del xi. But we know that the gradient of f with respect to a vector is the collection of row vectors of the partial derivatives. Each partial derivative del f upon del xi is itself a column vector. Therefore, we obtain the gradient of r to the power n power with respect to x by collecting these partial derivatives. So our gradient will become del fx upon del x1, because it is the collection of partial derivatives. So we can collect all the partial derivatives with respect to all the variables of x, x1 up to xn. But here fx is also m dimensional. So in each case, we have to find the partial derivative of each f from f1 to fm in this column. And similarly, this column is for f1 to fm with respect to x2, and this column for x3 and up to xn. This column will for f1 to fm partial derivative with respect to xn. So this is our the gradient of function f r to the power n to r to the power m. This belongs to the dimension m cross n matrix. So this is the gradient of vector valued function. Now the next topic in this series is the Jacobian. Jacobian is similar kind of, is a gradient, but it tells us the collection of all the first order partial derivatives of a vector valued function. That is called the Jacobian. So the Jacobian J is a m cross n matrix, as we have seen in the previous question. These all are the first order derivatives of this first order partial derivatives. So it is the Jacobian. So Jacobian is nothing but it is the gradient of function dfx by dx, and it is the collection of all the partial derivatives that I have written in this matrix from of fx from x1 to xn. I have made the partial derivative. This is the Jacobian. But if f is m dimensional, then each f is m dimensional. This is the Jacobian of this function. So if we can generalize the Jacobian at any ij in the matrix ith column and ith row and jth column, then this formula will find the at each point in the matrix, each element in the matrix of ith row and jth column, del fi upon del xj. This is the gradient Jacobian at each ij. Now, the determinant of Jacobian of a function can be used to compute the magnifier between the two areas. Let us say this is the blue area, this is the orange area. Blue area has the dimensions of b1, b2, and it has c1 and c2. So it tells us the magnification of the area. That means area and volume. That means the volume of region 2 upon region 1. This kind of things we used in the Jacobian. Determinant of Jacobian will give us the magnification of two areas. So the absolute value of determinant gives us the scaling factor. Let us take an example on this quickly on the Jacobian. Fx is equal to ax, where fx is given as m dimensional and x is given as n dimensional and a is given as m cross n dimensional. So f is r to the power n to r to the power n. To compute the gradient of this function with respect to xj, first of all, we write our function in the general form as f of ix is equal to summation j is equal to 1 to n aij xj. And we know that del fi upon del xj, that is, if we partial derivative with respect to x, then it will give us a, only a with respect to x. So with respect to xj, del fi, it will give us aij. If we expand this and we find the partial derivative, then we will get aij. Df by dx is nothing but it is, we know that it is the partial derivatives, collection of partial derivatives. And in the previous, we have seen df by dx as this. So df1 by del f1 by del x1, we can find this from here. This comes out to be a11, this comes out to be a1n, this comes out to be am1, and so on up to amn. So this will become our A matrix, which is of m cross n dimensional matrix, after finding the gradient of this function fx is equal to ax. So the last topic of this is the gradients of matrices in this concept. We are interested in computing the, till now we have seen the gradient of vector valued function, univariate functions, multivariable functions. Now we will do the gradient of matrices. We are interested in computing the gradient of this matrix, let us say A matrix, which is of 4 cross 2 dimension with respect to a vector x that is 3 cross 1 dimensional. We know that the gradient dA by dx, it will the 3-dimensional space 4 cross 2 cross 3. The dimension of the gradient of this matrix will be 4 cross 2 cross 3. How to find the gradient of this matrix? There are two approaches available for to find the gradient of this matrices. First approach is collating the partial derivatives into a Jacobian tensor. First of all, let us consider this matrix 4 into 2 in which the 4 rows and 2 columns are there. And the second one is which we can say that x vector dimensional with 3 rows and 1 column. So in this approach number 1, collating partial derivatives, first of all, we will find, because our x is 3-dimensional, so we have to find the partial derivatives with each x, like del a by del x1, del a by del x2, del a by del x3. So here we find the del a by del x1, which comes out to be 4 into 2 matrix. Here del a by del x1. The next step is del a by del x2. This also comes out to be 4 into 2 matrix. And del a by del x3, this also comes out to be 4 into 2 matrix. So first of all, we have to find the partial derivative with each x. After that, we will collate these partial derivatives, del a by del x, which belonging to 4 into 2 into 3. This will become our 3D space in which 4 columns, 4 rows, 2 columns, and 3, we can say that in the z direction. So this will become our 3D space So this is the approach number 1 to find the gradient of this matrix. In this approach, we compute the partial derivatives del A by del x1, del A by del x2, del A by del x3, each of which is 4 into 2 matrix, and collect them in a 4 into 2 into 3 tensor, which is also called as Jacobian tensor. So this is the approach 1. Now let us move towards the approach number 2 of to finding the gradients of this matrix. So approach number 2 tells us the first of all flattening of the matrix into a vector. This is our first step, and after that computing the Jacobian matrix and reshaping into a Jacobian tensor. Let us see how. Let us consider a matrix A which belonging to 4 cross 2 dimensional matrix. First of all, it is said that we have to flattening this matrix into a vector. So first of all, we are reshaping this matrix into a vector. So we are converting this matrix into 8 into 1 dimensions. So 8 rows and 1 column. After that, we are going to find out this gradient with respect to this x. That will comes out to be 8 into 3 dimensional vector, 8 into 3, because here our x is 3 dimensional. So 8 into 3. After that, we have to again reshape in the 3D space 4 into, we can write 8 as 4 into 2. Again, we have to reshape this matrix in the original form. This is our last Jacobian tensor. So this was the approach number 2 to find the gradient of matrix by flattening the matrix. So as we have seen that the gradient of matrix with respect to vectors, which results a multi-dimensional vector. In the above example, we have seen it will be the 3-dimensional vector. Suppose if we compute the gradient of a matrix M cross n A matrix with respect to the another matrix which comes out to be P cross Q matrix B, the resulting Jacobian will be 4-dimensional, that is M cross n cross P cross Q. That means a 4-dimensional tensor Jacobian, whose entries can be find out by this formula at any point ijkl, that is del aij upon del bkl. So let us see an example on this topic, gradient of vectors with respect to the matrices. So let us consider a function fx, that is ax, in which f belonging to r to the power m, that is m dimensional, and a is m cross n dimensional, and x is n dimensional. So df upon da, that will come out to be f is m dimensional and a is m cross n, that will come out to be m cross n dimensional. So by definition of gradient, we know that the gradient is nothing but it is the collection of all the partial derivatives. So df upon dA, it is the collection of all the partial derivatives, df1 upon dA, del f1 upon dA, del f2 upon dA, up to del fm upon del a, where each del fi is 1 cross m cross n, because each a is m cross n, so each del fi is of 1 cross m cross n dimensional, because we know that each a is m cross n dimensional. So as in the previous question, we can write our function in the general form as summation j is equal to 1 to n, because our x is n dimensional. So we can write summation j is equal to 1 to n ai is a, where I is 1 to m. So at any point del of fi upon del of aiq,
Yeah, you are not audible, Kapil. Yes, Priyanshu.
Sir, I'm trying calling Kapil. He's not connecting.